Great. Telling us about orders, distortion, and regularity.
Thank you very much. Thank you for coming. And what I plan to do today is to elaborate on a question that I asked last week during the meeting process. I don't know if you do it. But now I will try to emphasize how the relevant. The one is going in many directions. So I will just first in the framework of orderable groups, then I will put some regularity and I will explain why it's important to look at this question on the framework of group acting by or regular maps. So the question is the following. We define the notion which is involved, but let me ask the question immediately. So the question is, does there exist a finitely generated group which is left orderable, having only distorted elements? Okay, so this is the motivation for me. So let me recall a little bit what is this notion of distortion.
All of this should be distorted or
No. The elements.
I know, but all orders are like that or
No, the group is left orderable.
The distortion is not an orderable property.
Yeah. No, you are thinking about the distortion of the element.
asking, should all orders be like that or there should be one order like that?
One of the because I imagine that for another. But let me remind you of this. So you have a finitely generated group, generated by F1 and F3. And to every element in the group, you can associate the word length with respect to the system of generators, which is just the minimum of factor you need a factor among the generators and the inverses. We need to write this element for this I1 up to 8 plus or minus 1. Okay, and these are elements in the final set of generators. The set of generators is specified. So you have a word length which depends on the system of generators, and this satisfies some inequality, which is obvious. The fact that the word length of the product is smaller or equal than the sum of the word length of the elements. Okay, which is obvious because any expression for F and B and you combine them, then you get an expression for the product. So you can look at this limit of the growth of the word length of the powers of the element. This has a limit, and whenever this limit is 0, one says that the element is distorted. And the point is that, but the word length depends on the system of generator, but this property doesn't depend. The property of being 0 or non-zero doesn't depend. Okay, and somehow what it says is that the growth of the group word length of the powers of the elements is sublinear, and it says that there are many relations in the group, so that there are ways to write the powers in as expression of the smaller word length. Okay, again, I will motivate this with an example, which is very important in this framework of action from one-dimensional spaces, even in the framework of the orderable group, which is a bounded solitary case. So we take the bounded solitary group generated by two elements, F and B, where the conjugate of G by F equals the square of G. In this group, the element G is actually very distorted because this equality implies that if you conjugate G by F to the minus n, you get G to the power 2 to the n. So that the word length of this is linear, it's not exponential. And actually, using this, one can show that in general, the word length of G to the k is about logarithm. So this is really very simple. So you divide by k, you get that is limit for G equals to. Okay, well, this group is very important because in this level, because we did arise is not very. As I look back on the line, this is a target with the group of a fine transformation in the line. So there is this question. Now the point is that in this group, well, she is very distorted, but F is actually is not distorted. And the question is whether there might be something which is orderable and where everything is how counterintuitive because you have pattern which is order. I would like to say, well, if the maximal element for an order should know everything, so it shouldn't be distorted. But that's what my guess is that this kind of issue exists, but I will expect that if they exist, then they must be very complicated. Of course, they must be because it is already difficult to build examples of torsion free groups for which all the elements exist. But this is very well known. I mean, techniques of taking extensions and so on. You get something that it is has the property, but only torsion. It also follows from it doesn't work opposite. The remarkable work opposite. But the point here is to make it record. Okay. There is a very nice example by Rivas and Destino. It doesn't answer the question, but it is much better than this. It is the human group. So the human group is a group generated by 4 elements, A, B, C, and D, where you have this relation for all the generators in a cyclic way. So, say, B conjugates A square, C conjugates C to the square, D conjugates C to the square, and finally, A conjugates B. So because of these relations, all the generators are distorted. But actually, there are elements here which are not distorted. But what is nice is that this group is not only torsion free. So the theorem of Rivas and Destino, so let me erase here, so because this is actually a theorem. This is part from the trivia is that the human group is left orderable. Okay. Again, this is not obvious at all. If you take a presentation and you try to build an action on the real line, it's not obvious. And there is a very, very nice argument using this kind of bounded solitary group which are inside. We take the firing actions on the real line, and actually there are other actions for the bounded on the line, and we pass together them. And the point is, because of this cyclic relation, you have to do it infinitely many times, okay? In a somehow cantorial way. So you managed to do it, and it's really very, very nice. But again, it doesn't answer the question, but at least we have something where the generators are, which is not the case for the bounded solitary. Okay, now I will explain why such a group exists, why it should be very complicated. So the remark is, let me call such a group a left orderable distorted group. So if a left orderable and finitely generated distorted group exists, then all left orders on the group are very special. So all left orders are what are called type 3. So I will explain the terminology here. But type 3 essentially means that the dynamic on the real line associated to their dynamical realization are very complicated. So again, when you say there is this Folklore lemma, which says that if gamma is actually countable, but I will refer to the case of finitely generated group, gamma is the orderable if and only if it acts by orientation to certain homeomorphism of the real, with no, well, it acts faithfully with no global fixed point. Okay, and for the case for general action of homeomorphism with the property for finitely generated groups, there are 3 types of actions that may arise. So type 1 is somehow the kind of actions that arise in the theorem that Cristobal Rivas explained yesterday. Type 1 are actions which are semi-conjugate to actions by translation. Okay. Okay, which in a very large sense, in the sense, maybe this is not the right word, but if there is an orbit which is split, then you are type 1. Okay, this is included. Type 2 is corresponds to the set of orders which are not of type 1, but or that the action that somehow come from an action of the circle, which means that there exists a homeomorphism of the real line, no fixed point at all, say moves everything to the right. No, this is okay. That commutes with the action. So for instance, you take any group acting on the circle, you take the lift to the real line, you get another group that acts on the real line that satisfies this problem. Okay. And type 3, what is type 3? Not of type 1. No. Okay. But the point the definition. Okay, but the point is that for type 3 orders, one can look something. There is some chaotic behavior in the sense that, and this is a proposition. This is very interesting because if one goes back into the literature on this, there is a close related classification by, I think by Pollard, that in the framework of lattice orderable group. There is also some work by Malutin on this, but anyway, the proposition is that for type 3 orders, you will assume that the action is minimal. Otherwise, there is somehow like one linear interval that one can collapse so that it becomes minimal. Okay, so if the action is minimal for every pair of intervals, there exists an element in the group that sends the first interval into the second. So it's a very contracting action. Okay. So this is the case, for instance, for groups here. So this is the case for the affine action of the bounded solitary group. But actually, there are actions of the bounded solitary group, for instance, those that come from the orders, which do not have this property. Okay. And let me just mention that it's already difficult to produce examples of left orderable groups for which all orders, all actions on the real line are of this type. Okay, this is a theorem. Well, there are the remarkable examples by Hyde and Lothar for finitely generated left orderable simple groups, and with Rivas, we prove that for these groups actually we have this. Okay, for the Hyde and Lothar groups, all left orders are of type 3. Okay. Yes.
Well, for type 1, I see you have an alien quotient, but for type 2, how do you rule that out? Like a group with every element is sort of can't be alien quotients, or
Okay. Yeah, because that's true. Yeah.
how do you rule out type 2?
To the distortion property. Yeah. Okay, because it is important. Here I assume that it is finitely generated. So if you take, you're right, but so if you take an element in the group that moves everything to the right more than one, then it cannot be distorted. Because then it keeps moving too much to the right. So it cannot be. Okay, so you can conjugate 5 into the translation by 1. Okay, so let's suppose that 5 is the case. No, 5 is that's important. But 5 is not necessarily a leaf or an element in gamma. It's just a homeomorphism that commutes with the action. Okay, but you can conjugate the action so that 5 is the translation by 1. Now, if you do that and you take an element that moves everything to the right more than 1, it cannot be distorted. Because okay, it needs some argument, but this is the kind of thing that one has in mind in order to think that groups with only distorted element cannot exist because the largest generator cannot be distorted. And actually, this argument is not correct, but it's correct in this case. Okay. Yeah, midpoint. Okay, well, and there is this theorem. 21. And well, this shows that it's very difficult to do. Okay. And if there is an example of left orderable distorted group, then it should be like. Okay. But unfortunately, I cannot talk about the question, except for that I think that it's an interesting question. But I will try to say something in the regular setting, and I will show some variation of this question, and I will explain why they are still interesting. And actually, we concentrate on some specific case, which is the case of germs, more than action. So I will add some regularity. And here there are many words, remarkable words. Some of them in the one-dimensional setting, some of them in general. It's a very similar work by Caligari and Friedman. And then work by Man and then Yahoo and Caligari and Russell and many interest on the notion of distortion for groups of transformations, and it's also the work of Orderable. And I will concentrate on a very nice construction by Atelier, and also another related construction by other names here, Finitely and Zare. Okay, so I will discuss this. So the idea now is to put some regularity. Instead of taking groups acting by homeomorphism, I will consider group acting by homeomorphism and consider the notion of distortion. Okay, but and here what is interesting is that the notion of distortion is immediately related to derivatives. Correct. So, for instance, let me give an exercise. So, I think this is written nowhere, but I was told by people that it was an exercise. Let me define something before. So, because here the notion is what's introduced by Yomo. The right notion is not a distorted element, it's a distorted element. So, if you take a G, I generate you an element F in G is a distortion element if there exists a finitely generated value where F sits inside as a distorted element. Okay, okay, and this note makes sense for any kind of group. And it's finitely generated. You look at finitely generated subgroups. For instance, this is the exercise. Every homeomorphism of the Cantor set is a distorted element. If someone knows a reference for this, it would be very useful. But it is natural to expect because this group is very big. So every homeomorphism of the Cantor set is a distortion. But let me give an example where you define something. You have a criterion for a element to be undistorted. It is very simple. You take the group of C1 diffeomorphism of any space, take an element with an hyperbolic fixed point, then F is undistorted. Okay. F is not a distorted element. I will say that it's undistorted. And this is obvious because if you take since it is hyperbolic, if you take the growth of the logarithm of the derivative at the fixed point, it grows linearly, and therefore the one line cannot grow sublinearly. Okay? Somehow. So, and there are some extension of this. So, for instance, the paper of Atelier and Friedman, there is this claim that if you have a diffeomorphism manifold and it has some Yakurev exponent which is positive, then it is also distorted. But actually, let me express this part here. So if you take a C1 diffeomorphism manifold with positive topological entropy, then it is undistorted. And well, this is not hard at all. I mean, it uses some classical inequality in this setting, which is the Williams inequality and also regularity. I wanted to say, in order to show that in this setting of regular maps, the notion of distortion applies to something, to elements, to maps which are somehow elliptic. And in this setting, there is a very nice construction by Atelier. It's a theorem, but it's not a construction because it links the finitely generated groups associated to the distorted elements. So the theorem of Arthur says that if you take rotation of the circle of the rational angle, and you look at inside the group of diffeomorphism of the circle of scenes in regularity, it is a distortion element. Okay? Every irrational rotation is a distorted element of the group of scenes in diffeomorphism. So given an irrational number, one can build finitely many generators. Actually, the number of generators doesn't depend on the angle. So that one can write the specific powers of the rotation so that it comes very close to the end. Actually, he proves for the rotation and for many other diffeomorphisms of rational rotation number, but the truth doesn't work for every diffeomorphism of rational rotation number. It requires some dynamic conditions, so it is open actually. Whether this is true for every diffeomorphism of rational rotation number. Okay. And the theorem of Vanesti and Sarek is that again to take the rotation and then it is it's a distorted element of the group of piecewise affine homeomorphism of the set. It is also very necessary. Given an angle, but when we find in many piecewise affine homeomorphism, so that one can reproduce some powers of this rotation using it very few. Okay. This is a general construction. And again, this doesn't close the problem because I mean this is a definitely result, but it is still interesting to look at whether some specific rotation of this structure is some say generalized topic. Very interesting from a complementary. So again, this notion of distortion because of this proposition of this spirit makes sense in the elliptic framework, and even in this framework, it is still interesting to try to change the regularity and look at what happens. And the remark is the following: you can look at the given a manifold, you can look at the group of diffeomorphism of the manifold in different regularities. If you take CR and CS, and I will say that R is larger than S, then there is a strict condition between the group of diffeomorphism. So this group is larger, so it is easier to be discovered here. And the question is, so given R larger than S, does there exist F, which is a distortion element in the larger group, and F is undistorted in the smaller group? Okay, and again, this kind of question is very natural. And the idea behind this question is whether one can study somehow the geometry of these groups. These are very large groups, not locally compact and so on. And one would like to do some geometric theory on them. It becomes difficult because there is a theory by Rosenthal that allows to do that. But the theory of Rosenthal requires to detecting something which are called norms here. And he proves that they exist in some cases, but there is no explicit expression for them. So this is also related to finding the norms associated to the framework of Rosenthal. And here what happens if you go to the C1 category, the norm is just the growth of the logarithm of the derivative. Okay, so the again, this question I think is interesting because that's whether there are some derivatives up to some derivatives and some cycles and some chain rules that may fail to be true, but are true up to some error. Okay. This is very heuristic, but let me give an explicit result of it. Maybe try to. So the issues here are very hard to understand. So for instance, in the case of Avila, and now we know that rotations are distorted, that many diffeomorphisms are distorted, but we don't know of any diffeomorphism which is not distorted, having irrational rotation. Otherwise, you have irrational rotation number, you can add some hyperbolic fixed point, and you immediately know that it's very distorted. Okay, so the situation is very so. This is a very nice question. Take F as C1 diffeomorphism of the interval, but that's only parabolic fixed points. The question is whether it is distorted. In the group of C1 diffeomorphism of the we don't know whether the numbers of the obvious obstruction to distortion is it becomes very hard to do. And in higher regularity and in general manifold, actually we don't know nothing. The only thing that we know is that for the one-dimensional setting, which is again very special, one can produce something. One can produce at this level, at this level, one can produce a difference between the group of C1 and C2 diffeomorphisms. Yes.
What is a parabolic fixed point?
Parabolic means that the derivative equal to 1 at the fixed. And there might be infinitely many, but think about something very boring. Think about a map that moves everything to the direction to the right and has a parabolic fixed point here, so the derivative equals to 1. And a parabolic point here. This is like the element G in the boundary axolotl group, the smallest. The smaller element. The element G is like this. Okay. I don't know. So in many cases we know how to prove that it's distorted. But actually, even the question of whether for this map there is an associated map F such that F and G generate a boundary axolotl group is an interesting question, and we don't know the answer. This is always true in the continuous setting. If you have a map of the intervals, then you can build another map for which they generate a boundary axolotl group. And why is that? Because if you have a map like this, you can build something that conjugates this map to the square, as like you conjugate a translation to the square. Okay, you can always put some every homeomorphism in the real line is conjugate to this elementary. But in the C1 setting, this becomes a question of analysis, and it's amazing. Okay. Okay, let me state a theorem in order to show that this may be interesting. So I put this in some particular case, and it was sent by Dinamarca and Stable. And it says that there exists an F, say it is C2 diffeomorphism. Actually, it is a single diffeomorphism, such that F is a distortion element of the group of C1 diffeomorphism of the interval. This is what I proved, but actually Dinamarca and Stable managed to improve this to C plus anything in the middle, but not C plus 1 plus 1. And F is undistorted in the group of C2 diffeomorphism. Okay. And the reason how it is possible to put something like this is because there is no derivative. And again, this is very special of the one-dimensional theory. There is the classical derivative in order to deal with the distortion issue in the T1 setting. And in order to go into the security setting, you look at the affine derivative. So when you have F, the affine derivative is the quotient between the second derivative of the first one. Okay, and there is a chain rule for this. And the chain rule is V2 over D of the product is the sum. In that is, this is the chain rule for the Atelier. And now the point is that if you look at this function as an L1 function, right? Usually the C2 category is just look at the C1 norm. If you look at the C1 norm, well, this is a change of variable, so it doesn't change the value. So you can look at the following things. You take a differential and you look at the V2 over D L1 norm. And you get, so let me call this, no, this is not a good. This is a norm, and let me call this, and you get this inequality. And because of this inequality, you have something to deal with the distortion. So you can look at this number along the iterates of the model. And if this number grows linearly, then this element cannot be distorted. And the point is that this number can grow linearly even for diffeomorphism like this. Okay? And this is a very complicated issue that deals with the C2 category and iterated by environment introduced by your mother. And it's really something, but the idea is very nice. It's very simple. So you just look at some norm that unfortunately only exists in very low regularity and dimension. Let me just say that this comes from the historical work. The draw, because this is the variation of the logarithm of the derivative. Okay, and this is the way how to prove that something is undistorted, but actually then you have to manage to get something which is at the same time distorted with the group of C1. But this is not very hard, at least in the C1 category, but it is much harder in this. But what I want to emphasize here is that, well, this somehow solves the general question. Again, in a very particular case, the interval, regularity C1 and C2, but it requires the difficulties to be defined on the full interval. So I want to move to germs. And I want you to explain why this topic is still interesting for germs. And actually, it's very interesting and a very challenging. So germs are very important in this setting, and so I want to come back to the framework of orderable groups because I want to do a remark. It's a nice remark because we started with Atelier last Friday, and okay, we shouldn't forget that the group of germs is also orderable. So the prototype of the universal model for orderable groups is the group of homeomorphism of the. Okay, and we have this postgraduate result in that at least every countable group inversity. Okay, which is reported. So this is reported. And now we can look at the group of germs. Germs means that germs are filled. The point. So the group of germs of at infinite of the orientation resulting from a map from Atelier. Okay. So these maps are not fully defined, they are only equivalence classes for polymorphism. Okay. But it turns out that this group is not orderable. Why is that? It is not obvious. So here I can produce the order with electricity. This dense sequence of numbers, and so these are what I call the canonical orders of the polymorphism. A dense sequence of points on the real line, and you compare the elements by looking at this. The point is that here the order is not existing, but it exists. And this is an application of the Bernstein procedure. Okay, they didn't prove that. Actually, the proof appears in our definition the Van and Riga, and it is a proof of this using this Bernstein argument. It is somehow the compactness argument. So, how do you order germs? Well, in order to order germ, you cannot fix a point to look at the action at this point because the germ is not defined. But you need to do it to take sequences from very quickly. and comparing along sequences. But then the comparison is not well defined because it may change from one point to another point. And then you pass to subsequences, and you continue doing this, and you do it only for finitely many elements, thanks to this algorithm. You only, in order to order a group, you just need to order finitely many finite subsequences. Okay, and it works. Okay, but I cannot give any explicit order because it depends on the sequence. And again, the sequence are taken in order to order finite subsets. And the compactness argument, or the bounce-rate argument at the end, gives an order on the group of changes. And now there is this remark with Michele. Is that if you take Omio and you look at the germs, say mai-May, this is the orderable, and germs plus infinite, there is a homomorphism into this problem. And the quotient are homeomorphisms that are compactly supported. Okay? And because of this, this group is orderable. And you can take any order here, and you can do a convex extension procedure in order to produce an orderable formula. Okay? And all orders in Omio produced this way are different from those that are produced using sequence. Because in an order that is produced using sequences, this group is not convex. And I think this is a much clearer answer to your question. Okay, so this is a full family of orders which are not a standard in this numerals, but they are still in the closure of the standard orders. Okay, so the question of whether the standard orders give a dense subset remains open. This is okay. Again, this is a remark essentially by Michele last week, and okay. So this was just to emphasize. This was because of the question last week, and to emphasize the relevance of the group of germs in this. And now let me come back to the regularity issues. And what about distorted germs of regularity? And again, I come back to my favorite example. So take g of x equals to this germ. I will consider germs at the origin because it is easier to manage to explicit formulas. So germs at the origin. Okay. So I take this germ. Well, for this germ, if you consider the hyperbolic germ multiplication by 3, depends on the coordinate you are taking, then these two maps generate a bound accelerator because you are looking at the copy of the affine group at the origin. You are moving the infinite to the origin. Okay, so the tension G F equal to this. So this is in the group of say of real analytic or even in this case in the set of real analytic different germs of different basis. So these 2 points. And this has a very nice formula. This is x minus x to the square x. And the question is, if we take any other germ, say parabolic germ, which means that the coefficient here is 1. The derivative of the origin is 1. What are the distorted germs? Okay. And because we are dealing with germs, we can't do this kind of stuff because here we're reading the argument to be defined on the perimeter of manifold. Here we are dealing with only a germ. Let me ask a very complete question. So take this germ. So take h of x equal x minus x to the square. Is it a distortion? A distortion element in the group of germs of say real analytic with one small interval in a group of germs of C infinity with one small interval, etc. Okay, so for this element, it is impossible to produce an F at least if it's real and needed. This is very well known. I will explain this. Okay, but it is not obvious. This doesn't answer the question whether it is distorted or not, because this is the easiest way to show that something is distorted. That actually proves that it is very distorted. Okay, and I think this is the mention. You can ask this question for any parabolic general. To be completed, let's consider this. Okay, and the difference here is that so here there is some coefficient, and here there is no coefficient. They are really very. Okay, and well, this is joined well with the LNR. We look at some very good literature on this kind of stuff, not on the framework of distortion element, but on the framework of the mathematics and so on. And it turns out that there is a result by Firmo in the 80s, and which also follows from work of the world. In his thesis, it's about 2, I don't know. Okay, in the 80s, which says that something which is not obvious at all is that this map H, this gem H, and this and G, and C1 conjugate. They are C1 conjugate. And actually, any two parabolic gems has C1 conjugate. So C1 conjugate is not very strong condition. And since G is distorted here in the group of analytic gems, H will be distorted in the group of C1 gems. Okay, and let me explain why this is. So, but C and H are not C3 conjugates. I will explain this. Why are not C3 conjugates? Because of the difference of this topic. You can check it by just by looking at the formats at the Taylor series expansion. You take some, so you guys have classic field, you do the corresponding multiplication, and you get a conversion. So they are not typical. But a better way to explain this, what is happening here, why they are not conjugate, because there is still another derivative, the fraction. Fraction. There is the fraction derivative. Now, for the fraction derivative, there is also a cosine relation with at least with the square of the derivative. But since we are dealing with parabolic germs, any conjugation between them has to be parabolic. This is so in that case, the fraction derivative at the origin becomes a group homomorphism, so that they cannot be conjugated. Otherwise, they will have the same fraction derivative. And let me just finish by stating a theorem, which is much more general than this, and but we was the reason why we started thinking about this kind of thing. Well, the question in the middle is solved. So, have they simply conjugate or not? Okay, and it is not. The answer is not obvious at all. And the theorem is really something new. Is that in this case, G and H are not, which is very strange. It says that somehow the traction derivative, which is only defined with a T derivative, is actually invariant on the C derivative. And this is the phenomenon. Okay. Again, traction derivative, you require T derivative in order to define it. So it is invariant on the derivative and the parabolic derivative. By C3 maps, but what they show is that it is happening and conjugated by parabolic C2 maps. For those maps, you cannot do the change. But actually, what we discovered is that follows from work of the person. So there is one of the appendices in the history report where we proved that for maps like this, there are vector fields which are associated, and then the vector fields have certain regularity. And well, we claim that if your model is of class CR, then the vector field is of class CR -1, and this is not enough to prove this result. But actually, if you go into the proof, you will detect that it's not even only of class CR -1, but it's of class. It has another derivative operation. So, okay, this we discovered after having after provision approved by ourselves, and the point is that the Schwarzen derivative, as this is somehow well known in studying, measures how far you are from an affine map. This is more or less the result. And actually, this theorem is much more general. There is a much more general version. There is something which is called even a germ of diffeomorphism. There is something which is called the residuum, which is the only term of the Taylor series expansion that one cannot feel using formal conjugacy, and we proved a theorem of invariance of this under low regular. Okay, but actually the proof of this general statement that I will not give in full generality. It is the same as for the theorem of the invariant of the class and the derivative by okay, and coming back to the distortion problem, or to finish is, well, the conclusion is that we don't know whether this H is distorted in the group of C2 germs. What we know now is that one cannot prove them using this trick. Okay, because H and H to the square will not be conjugate. Otherwise, there will be some contradiction because the Schwarzen derivative of H and of H square are not the same, so there will be some contradiction, and it is the full Schwarzen derivative which is invariant. Okay, so we don't know anything. The only thing that we know is that the easiest trick to prove this something doesn't work, at least a type of regularity, but it works in this one regularity because of this theorem of the. Okay, I will stop here. Thank you very much.
Questions? Okay, well, I have a question.
Yes.
All right, so when you're thinking about the distortion of elements of omega plus R, you have this sort of natural filtration by elements of sort of increasing regularity where you, so what I mean is you have this example where you looked at an element of a C2 map of 0, 1 that was undistorted, but then it became distorted when you considered it in C1 plus alpha maps. So you have this filtration where you look at elements that are further down and you see that they become distorted higher up in the filtration. If you're thinking in a general sort of complicated enough left-orderable group, are there any sort of filtrations that you would expect or be useful? Where you see like an algebraic filtration of a left-orderable group where you kind of do the same kind of trick.
Very good question. Yeah, it's a very good question.
Yes, I have a very big question. So first you try to talk about the James at infinity and now how you switch to James at 0. So is there some similar phenomena you try to focus on James at infinity? For example,
Yeah. No, it's exactly this. If you look at germs of infinity, this is multiplication by 2. This is why I said multiplication by 2. But at the beginning, this is multiplication by 2, and this is the translation. So the conjugacy here is x into 1 over x. This is the conjugacy. So this is really the conjugates of the generators of the Pavlov solitary group independent. This is why you have this property. You don't really need to check it.
so same statement also happens for the very last
No, there is an issue. Yeah, thank you for that. No, because here you need regularity as a fixed point. It's these kind of things are very, very sensitive.
Any other questions? Let's thank the speaker again.